Welcome to Miss Hammarlund's science class. Today, we will be learning about stars.
Haven't we talked a bit about stars already? I mean, we learned about our star in a previous lesson.
You're right. We have talked a bit about the sun already. However, don't you want to learn more? There is so much in this universe to learn about.
Yeah, you're right. Can I help?
Of course. Get up here.
Why don't we start this lesson from the beginning of a star's life cycle? A nebula is an interstellar cloud of dust and gas. In the nebula, a protostar forms. A protostar is a contracting mass of gas. This is the stage that a star is in before nucleosynthesis begins. What in the heck is nucleosynthesis? Nucleosynthesis is the formation of atoms that are more complex than hydrogen. So it's nuclear fusion.
You're getting ahead of me, girl. We'll talk about nuclear fusion more in a bit, but for now, let's finish talking about the life cycle of a star.
Okay, so what comes next?
There are actually two routes that a star can take, depending on its mass. For now, let's talk about the route that most stars take. Most stars end up becoming main sequence stars, just like the sun. You know it! The majority of stars are main sequence stars. A main sequence star is a star that is fusing hydrogen in its core.
I knew that. And when a star runs out of hydrogen, it becomes a red giant, right?
Yep! Red giants use up the helium that was formed in their cores from nuclear fusion. After all of this helium is used up, a star loses its outer layers and all that remains is a small, dense star known as a white dwarf.
You mentioned earlier that there's another route that stars can take. What is that route?
Sometimes a protostar will become a red giant instead of a main sequence star because large stars use up so much energy compared to smaller ones. Eventually, these stars become supergiants. Supergiants keep using up energy and can create elements up to atomic number 26, iron. When a supergiant dies, it will explode.
The explosion is called a supernova, correct? That would make sense. Supergiant, supernova.
You're right, and that's a really good way to remember it. Here's another fun fact. Supernovas are actually what cause black holes and neutron stars to form.
Nice. Shouldn't we review nuclear fusion now? You have talked about it quite a bit already.
Well, you seem to know about it, so why don't you explain?
Miss Hammarlund, you can't get me that easily. Nuclear fusion is a reaction that occurs inside of a star's core. For example, the nuclei of hydrogen atoms are slammed together, forming helium. This releases energy in the form of photons. These photons will pass through the radiative zone and the convection zones of a star, eventually reaching the surface. It takes millions of years for photons to reach the surface of a star, possibly even billions of years if the star is big enough.
Holy guacamole, you are right on the money. Let's move on and talk about the different types of stars.
We literally just did that.
This is a little different from what you're thinking of, Jenny. There are 7 main types of stars, and this is going in order of decreasing temperature. O, B, A, F, G, K, M. These types are in reference to a star's spectral class.
What in the world, or I guess universe, are you talking about?
Don't worry, I'll explain. A star's spectral class is determined by luminosity, temperature, and size. Maybe if we go down the chart, it will make more sense to you. An O star is a blue star that is over 25,000 Kelvin in temperature. Their average mass is 60 times greater than that of our sun. As for luminosity, if the luminosity of our sun is 1, then the luminosity of an O star is a whopping 1,400,000.
Why don't you just say brightness instead of luminosity to make your life a little bit easier?
Jenny, I'm really glad that you asked me that. Brightness and luminosity are 2 different things. The brightness of a star is how bright it appears to be from Earth, while a star's luminosity is how much light it is truly emitting. Basically, the difference between brightness and luminosity is that luminosity does not change with distance.
Alright, that makes sense. So what about B stars?
B stars are also blue, but they are smaller and cooler, with an average mass of 18 and temperature of 11,000 to 25,000 Kelvin. Their average luminosity is 20,000. Moving down the chart, A stars are also blue stars. Their average mass is 3.2, and they have a temperature of 7,500 to 11,000 Kelvin, and an average luminosity of 80.
Where do these stars land on the HR diagram? I at least have an idea of what that is.
Well, let me finish talking about the star types before we move on. Next up, we have F stars. F stars range in color from blue to white. Their average approximate temperature is 6,000 to 7,500 Kelvin. They have an average mass of 1.7 and an average luminosity of 6. Moving down the chart, a G star is a star like the Sun. They have an average surface temperature of 5,000 to 6,000 Kelvin, a range in color from white to yellow, and an average luminosity of 1.2. Next up is a K star. These stars range in color from orange to red and have an average luminosity of 0.4, an average mass of 0.8, and an average temperature of 30,500 to 5,000 Kelvin.
I need to think of a way to remember these. Holy crap!
Finally, an M star is red in color. Their surface temperature is under 3,500 Kelvin. They have an average mass of 0.3 and an average luminosity of 0.04.
Oh, be a fine girl. Kiss me.
What?
Oh, I just thought of a way to remember the order of the spectral classes.
I'm gonna have to steal that one. Now, on to the HR diagram. The Hertzsprung-Russell, or HR, diagram is a graph used to classify stars according to their luminosity, spectral type, color, temperature, and absolute magnitude. Stars that are using hydrogen as power lie in the main sequence according to their masses.
I never thought stars, of all things, could be so interesting.
Well, there you go. And there's the bell, everyone. Have a great day and stay bright.
You suck!